Hello everyone, so in this video we will be discussing logarithmic differentiation. So this is also different from the one that we have discussed from the previous discussion, which is the derivative of logarithmic function. This one, the logarithmic differentiation, is about a variable which has a variable exponent. And the technique in solving this kind of problem is to take ln both sides before differentiating. So this is some of the examples of the logarithmic differentiation. First, we have finding the dy over dx of this problem, or the y prime. So we have y is equivalent to ln x raised to x. So as you can see, the base has a variable and the exponent is also a variable. So in solving this kind of problem, we have to take ln both sides before we differentiate. So that being said, we have ln y is equivalent to ln of ln x raised to x. Then, since we've already take the ln both sides, you have to remember or apply some properties of natural logarithm, which is, if you can recall, this is ln a raised to n. If this is the property, this is equivalent to n ln of a. So this is one of the property of the natural logarithm. So you have to also apply that here in our example. So we have ln y is equivalent to the power, which is the x. So we have x ln of ln x. So after we have applied the property of the natural logarithm, we can now differentiate our equation. So deriving ln y, so if you can recall, the derivative of ln u is du over dx all over the original value of u. So from here, our ln u is y. So we have y prime, the derivative of y is y prime, all over the original value, which is y. And then for the other side of the equation, we have x times ln of x. So if you can observe, this is two terms. This is composed of two terms. So let's say this is our u and this one is our v. So we can apply the product rule. So in product rule, we have u dv plus v du. So copy the u, derive our v, and in which the derivative of our v is the derivative of ln x, which is 1 over x, all over the original value, which is ln x, plus our v, which is ln of ln x, times the derivative of our u, which is 1. And then afterwards, simplify our equation. We have y prime over y. On the left side of our equation, we have x times 1 over x ln x. Okay, for this one. And we also have plus ln of ln x. Then afterwards, we can cancel this x here and the x in the denominator. So what we have left is 1 over ln x plus ln of ln x. And you have to remember that we have to find our y prime. So in order for us to isolate the y prime, we have to multiply both sides by y. So we can cancel the y here. So this would become y prime is equivalent to y times 1 over ln x plus ln of ln x. And then you have to substitute back the original value of our y, in which that is equivalent to ln of x raised to x. So we have ln of x raised to x times 1 over ln x plus ln of ln x. And then, since we can simplify this further by distributing the multiplication, to the terms that we have. So we have ln of x raised to x over ln x plus ln of x raised to x times ln of ln x. So since we cannot simplify this anymore, meaning to say this is already our final answer. So we have here our second example. We have find the y prime from the equation y is equivalent to x raised to x squared. So as you can see, a variable is again raised to a variable. So in this case, we have to apply the logarithmic differentiation. And for the logarithmic differentiation, in order for us to begin, we have to take ln both sides. So we have to ln y is equivalent to ln x raised to x squared. And applying the properties of natural logarithm, we have ln y is equivalent to x squared ln of x. So after we have made this a linear equation, we can now derive. So the derivative of ln y is y prime raised to y. Y prime over y. That is equivalent to the derivative of x squared ln x. So again, from here, you can observe that this is composed of two terms. We have the u and our v. So applying the product rule, so we have u dv plus v du. We have x squared plus times the derivative of our v, which is 1 over x, plus copying the v, which is the ln x, times the derivative of our u, which is 2x. Then afterwards, simplify your equation. We can cancel 1x from x squared and the x in the denominator. So we have y prime over y is equivalent to x plus 2x ln x. Afterwards, we have to isolate our y prime. So we have to multiply both sides by y. So we can cancel the y in the denominator. So we have y prime is equivalent to y times x plus 2x ln x. Substituting the original value of our y, which is x raised to x squared. So we have x raised to x squared times x plus 2x ln of x. Then, simplifying this further, we have y prime is equivalent to x raised to x squared times x. So we have x times x raised to x squared plus 2x times x raised to x squared times ln x. So since, as you can see, they have the same base, which are x. So by imaginary, this x here has an imaginary exponent of 1. So we can still simplify this and we'll make this x raised to 1 plus the x squared. Then the other one, we have 2x 1 plus x squared times our ln x. So we cannot simplify this further, so this is now our final answer. So we are now on our third example. So we have here y is equivalent to x raised to e raised to x. So applying the same process, we have to take ln both sides. So we have ln y is equivalent to ln of x raised to e raised to x. So from that, we can apply again the property of natural logarithm, which is putting the exponent before the ln. So we have e raised to x ln of x. So after we have made this a linear equation, we can now differentiate. So we have y prime over y is equivalent to the derivative of e raised to x ln x, in which this is our u again, and ln x is our v. So copying the u, we have e raised to x times the derivative of our v, which is 1 over x, plus ln x times the derivative of e raised to x, which is just the same, e raised to x. So afterwards, we can simplify. We have e raised to x over x plus e raised to x ln x. Then we have y prime over y. And in order for us to isolate y prime, again, we have to multiply both sides by y. So we have y prime is equivalent to y times e raised to x over x plus e raised to x ln x. Substituting the original value of y, which is x, e raised to x times e raised to x over x plus e raised to x ln x. So if you can observe, there is a common value between the two terms. We can still simplify this by factoring out what's common. So that means we can simplify this by having y prime is equivalent to e raised to x raised to e raised to x times what is left in our equation, 1 over x plus ln x. So this is now our final answer. Last example from this video is y is equivalent to x raised to ln x. So using the same process all over again, we have ln y is equivalent to ln of x raised to ln x. We have ln y is equivalent to ln x of ln of x. Because again, we have to put the exponent before here. So we have ln x, then we have ln, and what's left is x. So from this, ln x times ln x, that is equivalent to ln squared x. So from that, after we have simplified, we can now differentiate. So we have y prime over y is equivalent to the derivative of ln squared x. So applying the power rule, we have 2 ln x times the derivative of ln x, which is 1 over x. Afterwards, simplifying this by multiplying both sides by y. So we have y prime is equivalent to x raised to ln x times 2 ln x times 1 over x. Afterwards, we can simplify by multiplying this. We have 2x ln x times ln x over our x here. And then we can still simplify this further. So we can put this x to the numerator but negate the exponent. So we can have 2x raised to ln x. And then we have the x raised to negative 1 for this one times ln x. So we can still simplify this because they has the same base. 2x ln x minus the, the exponent of the other x times our ln x. So this is now the value of our y prime. So that's it for this video. I hope you learned something, and I'll see you on the next videos.